Mike. It is quite common for me to do that. It seems. So again, I will be talking about lists, tuples, and slice objects, which are surprisingly interesting little fellas. And This will be on GitHub as usual. And I'll put that up fairly soon. Again, I've got the link to the Quick Python book. As I was saying to myself, but let me tell you now, I have agreed with Manning Publications to work on a version of what they call live projects. It will be video plus exercises for people to work on their own. And that will be doing things very similar to what these lessons have done. That will be in development over the next few months, but that will be coming out eventually. So it was, to be honest, doing these streams that really kind of helped me develop the idea, and Manning was interested in having something like that that they could offer. So that will be coming along. And now let me switch over to a bigger window. There we go. Other thing I wanted to mention, of course, you can, of course, find the PyCon online videos at the link there. But more important, PSF nominations are in. So the PSF board elections will be happening. There are a number of interesting nominees. You can go look at them at that nominations link I've posted there. And of course, that will be tweeted and sent out on the members lists and all of that. So if you can vote, and if you've been listening to me and you do any organizing or work for the community, I hope you are registered, set up to vote. But if you can vote, then you can start looking at those now to get a feel for who you want to elect. I will stop short of actually endorsing people. I will say that I really, really hope that people vote for board members to come from someplace other than North America. I think that's going to be one of my guiding principles, and I hope it is for a lot of other people too, because we need to spread membership in the board around a little bit. Okay, as usual, there is, the things that I'm going to be showing you here are not in any way intended to be production ready. If you understand them, you can certainly copy those principles over into production, but mainly this is for experimenting. Again, I encourage people to poke around in these things and see what's going on. And so this time I want to talk a little bit about lists, tuples, and slices. As it turned out, I kind of got myself a little bit into digging around in slices some, and it's actually, I don't know that I'd ever really looked at slice objects per se before, but we're going to look at those today too, because they're kind of interesting. And there are a certain number of, there are a certain number of features, I think, that are pretty interesting about them. So to start out talking about lists, what is a list? Well, I mean, a list is a built-in type. It's a sequence of items, and we access those things by an index number starting at 0. So all of this makes it seem like lists are so easy that, why are we even talking about them? And I hope by the time I get through all, I've shown you some interesting things about lists, and you will be up for poking around a little bit more. So if you look at a list, like here I've got a simple list, 1, 2, 3, 4, and we ask what type it is, it says it's list. Okay, that's kind of redundant, and we can do the same thing. Is it an instance of list? Yes, of course it is. And I guess I don't know that I've talked about this a lot, but it's not all that Pythonic to check for the type of things. Java, for example, checks types all the time. Sometimes it's called a look before you leap language. And Python tends not to. And it's more of an easier to ask forgiveness than permission. That is, we're not going to worry about whether it's a list or not. We're just going to worry about whether or not it does what we want it to. Will it behave like a list? However, there are times where you do want to check whether or not something is a right type. And when you do want to check the type of something, excuse me, you almost never want to use type. Instead, you want to use isinstance. If you use type, it will tell you yes, no, whether or not it is exactly a particular type. If you use isinstance, it actually lets you compare to another type. And if it's a subclass of that type, it will still count as being true. So it's a little bit more flexible. Okay. So if we use isinstance, which is what you would use more often if you were really going to be checking, it tells us that our list object is an instance of list. That's shouldn't be surprising. But now, we've been poking around at what attributes objects have, and I want to do that here as well. So when we do that, we see that basically our list instance has a lot of attributes, and it's got some of them that are not things you would find just in every object. So for example, it has a dunder contains, which, oh, excuse me, I seem to keep suffering from that. But dunder contains is what is called when we use the in keyword, is one in a list. That we call the dunder contains method. So that's something that lists and related types of collections will have, but other objects might not have. We also have here, we have del item. If we need to remove an item, we have get item, which we may have run across when we were looking at iteration, for example. So get item is what's called when you use the square brackets and say a list square bracket 0. That will call the get item method. So that again is something that's going to be more specifically, I'm sorry here, I keep jumping around, more specifically part of what is in a list as opposed to just every type. We have some other things. We've got len, dunder len. If we use the length function, the len function, we've got reversed, which is going to be unique to lists. We've got set item, which is used if we were to say a list square brackets 2 equals 3 or whatever. So we're actually changing an item. That's there. So we've got a bunch of those that are specific to list objects. We also have some methods that are attached to a list object that aren't the same as what you would find, but they're not special methods, magic methods. They're not dunder methods. They're just plain old methods. So we've got append when we want to add something. We've got clear to remove the contents of a list. We've got copy, count, extend. We've got index, insert, pop, remove, reverse, sort. So all of those are things that are part of a list and its underlying machinery. Okay, now that's wonderful. As we look at this here, you can also And this, back in the days of the earlier versions of Python 2, didn't used to be the case, but it's the case now in Python 3. You can also subclass list. So I can make my capital L list a subclass of list. And basically, if I just put a pass there, it really is the same thing, but now it's a subclass. If I wanted to override some behavior there, I could. For example, maybe I could make get item, under get item, check for types or something, so I could have a typed list. I don't know. There are various things you can do. So if I create that, I mean, again, it's not horribly surprising. Yes, my subclass here, a capital L list, is not technically a list. If I were to ask instead what type it is, it would tell me that it's of type capital L list, so it's not exactly a list. So that again is why you use is instance rather than type. Okay, well, let's keep going here. Now, there are other things you can do, and if you want to override, if you want to inherit from list and override a bunch of methods, you can certainly do that. The problem with doing that is that if you make mistakes, or you might have some unintended behavior where your list stops acting as much like a list as you think it should. That can be a little bit awkward. Let's say we change the dunder get item method, but we change it more than we really intend. Then, you know, it's not the greatest for figuring out what's going on, and you know, maybe we don't want to do that. Maybe we want to have the listy type stuff stay the same, but still be able to override how we get at that particular behavior. So for that, there is something called a user list, and it's in the collections library. And a user list is what we had to do back in the day before you could actually inherit from list. And that is, it's a wrapper around a list. So it will have a data method that is actually containing a plain old regular list. And then you can override all of the get sets, whatever, and that will sort of control your outside interface, but the underlying list that containing the data still behaves the same way. That's sometimes a little bit less surprising for people to use, and it's sometimes easier for people to reason about as they go through, not having to keep track of this thing where, yeah, we've got the data, but we've changed all of the ways we get at the data, and now we can't get at the data sort of problem. So we can do that. If we do that, though, as far as is a user list actually a subclass of list? It isn't. It's a wrapper around list, so it's not exactly the same thing. And I'll talk to you a little bit about that. But if I made a user list and I append one to it here, you see it behaves and it looks exactly like a regular list. You can't really tell from just the way it behaves, other than unless you ask, basically. So that's kind of all the same. Now, sorry for my flipping around. I always do that. Now, if we look at what a user list is, well, let's look at its attributes really quick here. We can see it's got some of the same things. It's got some different things. I mean, it's got this cast method here, but it's got contains. It's got get item. It's got the in place add here is for doing a plus equals on it. It's got an iter method, so it can create its own iterator. It's got various things like that. It's got a set item just like the other one, reversed. It's got all of the things that a list would have. And notice here that it also, though, has a bunch of things here. It's got some ABC stuff, abstract base class stuff. I'm going to talk a little bit more about abstract base classes here in just a few minutes. It's got the same append, clear, mount, count. But then notice it's also got a data attribute, which is the underlying list that it's got that it's sort of serving as a wrapper for. So if we were to go look at that, if you were to go and get that data element, it would be just an ordinary list there. So that's a little bit about what is a list. I want to start poking around a little bit more. Lists are interesting things. Lists and how they manage memory and performance and that trade-off are a really good study in how to handle these things. If you were with us last week and I was talking about the trade-offs for optimization, and I was sort of suggesting that, you can basically either optimize for memory or you can optimize for performance, but it's hard to optimize for both. Well, lists potentially can grow to be millions of items, right? And that raises a couple of questions here. We know that lists are a collection of pointers to other objects. We already kind of worked through that in some of the earlier episodes. But the list itself has to have enough space to hold everything. So it does stand to reason that a list of 1 million items is going to be bigger than a list of just 2 items, for example. And it's kind of interesting how Python manages that. The interesting thing about a list is that access times stay fairly constant as the list grows. So really getting item number whatever should be the same whether you've got a list of 100 items or 100 million items. Getting the same thing, like say getting the second to last item of the list should take the same amount of time in general. The bigger problem, of course, is when you keep adding to lists and they keep having to grow. And that's a problem because when we create this list, we have to, that is the Python compiler and interpreter behind the scenes has to allocate some storage space just for the slots in the list, never mind the variables that will be associated with those slots. And if the list grows a lot, it's inevitable that we're going to run out of space and have to allocate more space. The problem always with that is that when you allocate more space, you get into this whole problem in computer memory, which is that probably you can't just take the next chunk of memory because there's probably another variable or another object occupying that space. If you want to keep everything all together, that means you have to go get a bigger chunk that's free and copy everything over. And it's this copying everything over that can take a lot of time when you add things. And as you add more and more and more, you can end up getting slower and slower and slower and slower. So you can get kind of a geometric or even a quadratic time there if you're not careful. Now Python, we'll see, tries to manage this in terms of growing a list. And then, of course, the same thing is also true if you're deleting from or inserting into the beginning of a list. Adding stuff onto the end of a list is not so bad. When you want to stick stuff in the beginning of a list, that means that you always hit this issue with copying. You have to push everything up. So basically, okay, so we're going to get another spot. Copy, 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 insert. And same thing when you delete, we're going to pull it out, and that means you need to copy everything back down to fill the hole. So both of those things can take a lot of time. So I am going to kind of make another pass. Talked about them last week with DEX, double-ended queues, well, just sort of for comparison and to see how those work. But in any case, the first thing I wanted to show you was how lists grow. Now, we did this last time with this getSizeOf function from the sys module, right, in the standard library. And there, since we were trying to find out how much memory was occupied by the list and all of the list's contents and all of their contents recursively all the way down, we had to, use a special function that tried to recurse and all of that. And it's a kludge and it's not too great. In this case, though, I'm only interested in the size of the list object itself. I don't care about the contents. The contents can be of any size. I just want to know how much memory it takes for a list. Okay. Now what I've done here is, what I decided to do is I'm just going to increase the size of my list in powers of 10 and check and see how big my list gets. So if I make a list of possible powers of 10 range, basically, let's do 7 powers of 10 from 0 to 7. And then here I'm going to use that as the size of a range that I'm going to turn into a list. So, 10 to the 0 power is 1, 10 to the first power is 10, and so on. So we'll go 1, 10, 100, etc. Okay, so, I'd expect you to think about what's going to happen, but you have no way of knowing what's going to happen. So let's just go ahead and fire this and see. Okay, let me get that down a little bit more. So yeah, here we've got our powers of 10. And notice that they're not really proportional. So for one thing, notice that it takes 96 bytes to have a 1-element list. A 10-element list, that's 10 times as big, only gets 200. 1,000, or 100 rather, that's 10 times as big, still only gets 1,000. And then 1,000 gets 9,012, and then you get 10,000 is, okay, that's almost but not quite 10 times. And then it's going on here, it's going on here. So yeah, you're right. It's kind of, not exactly, but kind of 10 times each when the numbers get bigger. But when it gets smaller, it's not the case. And it's kind of funky, but basically, when you first create just a list without saying if it's empty or it's got just a few items, it's going to create space for, I believe it's for 8 elements. So I think that's, we're doing 8 bytes a piece for 8 elements. No, we're doing 12 bytes a piece for 8 elements. Never mind. Or there's some overhead that we're going to have anyway, and then there's some space. I don't know, but I think it's 8 spots. And then basically the reason it does that is to speed performance. So we're going to make it a little bit bigger so that we can do addition, we can append to it without having to make a new object. But when we get to a certain point, we're going to run out of space. When we get to that point where we run out of space, we're going to copy anyway. It's going to be copied into a memory space that has some extra space. And the first timer to it does that. It's about double. And then it starts dropping down. And in general, what it does is it will give you, when you start getting bigger, like you're above 1,000 items or whatever, the extra space it will make when it runs out of space through your additions and you need to add more, that extra space, it'll add 12% each time. And this is through experimentation, they found this has about the best performance in that it gives you a fair amount of space to add items without, for one thing, hogging too much memory. If we doubled it each time we ran out of memory, you could end up with gigabytes of RAM taken up and not being used. But the 12% is enough that you're not continually having to make another object. You know, the other end of the scale is each time I need to add an object, if I'm out of space, I add space for that object, for that slot, and only that. Then that means you're creating new objects all the time, and it's going to be slower. So, so that's sort of the reason behind that. It's, as I say, it's actually kind of cool because of this. In general, when you're appending, basically the amount of time it takes to append is kind of proportional to the amount of time it takes. So let's see here. I mean, I don't want to play with this function here. I should have deleted it. I want to do this one here. So I'm going to make I'm going to make a test function who's just going to append to a list. Okay, and I made, to start out with, a pretty big list here because I don't want that initial stuff to get in the way. Instead, I want to just consider everything starting on a list of about 100,000 elements. And let me see here. I think actually it's going to, what we need to do here is we need to actually move this down here. Because I want to refresh my list every time. I think if I left it the way it is, I would end up kind of skewing my results a little bit. And I don't want creation of a list of 100,000 elements to be part of my timing. So I'm going to just make a fresh A list every time in between my time it runs. So now, I mean, you can sort of see that as we append, it should, from what I've seen, let me move back up here. I get ahead of myself too many times. All right, now we're going to go down here. Okay, we should then sort of see differences in the time it takes to append 10 items versus 100 items versus just 1,000 items, etc. So that we can kind of see how this affects things. So I'm going to hit that. And I'm going to get an error because I didn't actually compile the first part. So, one moment, please. So let me do this part. And now let me do the time it part. So, we're taking, for 10, it took 9 microseconds. For 100, it took 99 microseconds. And we're still kind of grinding away here. So yeah, as you note there, Chuck, it's always a trade-off between memory and time. And here it looks like we slowed down a little bit. Let's see here, and that's a little bit more what I would expect. And let's see if I had any more. I think that was it. So that is roughly, and I would speculate here that the 28 milliseconds, when we're really expecting more like somewhere in the 10 to 20 range, is probably because something kind of hit my computer and made things slow down. So, if you're really testing this, you'd want to do multiple repeats of the test. But in general, we're increasing by a factor of 10 each time. These are also slowed down because as it did its various runs, that list became larger and larger with the additions. So if you really wanted to be accurate, you'd need to go back and think a little bit about how you were doing the test so that you wouldn't have the list itself continually being either added to or created for each run of the test. But in general, the main point is that adding to a list will roughly be proportional to the number of items that it needs to move around. Now, the other thing, last time we talked a little bit about decks. So decks are, let me go ahead and execute this so I don't forget. Decks are a double-ended queue, and they are not lists. They are instead a different structure that has been designed to work as a queue, because it's really easy to make a queue using just a plain old list in Python. You want to put something at the front of your queue. You can go ahead and insert it at position 0, which, as I said before, means that they're going to have to copy all of the other slots in the list over to make a space for it at the beginning. And then if you want to remove it, you can pop it at position 0, which means remove it from the beginning. And that again will have the same consequence of copy everything back to fill up the hole. So with a deck, it's got a couple of functions that are designed to take care of this and are optimized for this. So if you want to stick something in at what a lot of us would say is the beginning of the list, the left side of the list, however you want to look at it, there's an append left function or method. And if you want to pop something off of the beginning, there is a pop left, which is optimized for handling that. So what I've got here for my test list queue and my test deck functions, they both take a list and basically for 10,000 times we insert at the beginning. So the first time we insert, it's easy, it's empty, it's by definition at the beginning. But the next one we insert is before the first one, and the third one is before those two. So we're continually inserting at the beginning and having to push things over. And then we will pop them all off in the same order. We'll start at the beginning, and basically it's going to be a last in, first out sort of queue operation. And then we're going to do the same thing with a deck, with a double-ended queue. So we can have a look and see how this behaves here. Let me get us a little bit more space. And see what the difference is in performance. I showed this last time on performance, but I was going so fast that I don't think we really had much time to look at it. So we can take a second here. It takes it a little while, but it's not too bad. There we go, 124 milliseconds for using a list. And the optimized dec is about then, 15, 16% of that time. So yeah, you were betting dec is faster. You know me, it's way faster. And that's doing exactly the same thing. And again, as I was saying, a dec in many ways acts like a list, but if we ask is a dec a list, it'll say no, it's not. And this kind of brings up the notion of things that are sort of like lists but aren't, and how that plays in with Python's duck typing and things like that. So as I say, in general, we don't worry so much in Python about whether or not it is the thing, but we do want to be sure it behaves like the thing. And so in the later versions of Python, we have abstract base classes, which are just like abstract base classes in other languages, in that you can have abstract methods that you must inherit from it and then provide your own implementation and override the method in the subclass, or it'll scream at you and throw an error. So one of the things that we use abstract base classes for in Python is organizing all sorts of object behavior so that we can have things that kind of behave like another object. So let me show you what I mean here. So this is the collections.abc module documentation in the standard library. And it's got a number of different abstract base classes that then specify what methods need to be overridden and actually implemented. But then you know that you're going to have a standard set of features, and you can use that to kind of check and see if something is like a list or like a tuple. So I want to look here at a mutable sequence. So a mutable sequence is what a list is. Well, let me highlight that again, just so we're all on the same page. A mutable sequence is what a list is. And that means that it gets a bunch of stuff that it inherits, and then it's got some stuff that it has to have. So notice that the sort of methods that it gets as mix-ins or gets along the way, it gets everything that sequence has. So, here's sequence is another abstract base class. And it gets append, reverse, extend, pop, remove, and that in place add. Also, though, you can see it has its own abstract methods. These are the things that it must have in order to really be a mutable sequence. You need to implement your own get item, under set item, under del item, len, under len, and insert methods. So all of those are things you need to be a mutable sequence. And of course, if you're just a sequence, and that's what a tuple is an example of a sequence, then you have everything that reversible has, you have everything that collection has, and you do need a get item and you do need a len. Okay. And then you also get, since you're a collection, you end up getting contains and iter and reversed and index and count. And you can see these are the things that are in a collection. And a collection is sized, it's iterable, and it's a container, so it's got contains, iter, and len. Size is where we ultimately get len. Iterable is where we get dunder iter, and container is where we get contains. So all of these behaviors that work with various functions or operators on the object, all of these things are defined as abstract methods by specifying when you make an object what abstract base classes it's inheriting from. You can then make sure that you inherit the right behaviors so that your object acts like a mutable sequence, but does what you need it to do. So it's kind of an interesting rabbit hole to go down. So if I were to make import from collections ABC, and I was going to say, look, I want to make an ABC list that inherits from mutable sequence, because Naomi just said that lists are mutable sequences. That's what I want to do. If I were to do this, right now, any thoughts on what would happen? Language lawyers may have an advantage on this one. Okay, I have basically made a subclass of collections ABC mutable sequence. I've said pass because I just want to inherit everything. What's going to happen is, let's try it. I am going to get an exception, and that exception is because I have not implemented, and it will give me a list of what I needed to implement. Let's get down here. Can't instantiate, oh, went too far. Can't instantiate abstract class ABC list with abstract methods del item, get item, len, set item, and insert. In other words, if you go back over here to the other side, so in other words, these, the ones right here, that are the abstract methods for that. So yeah, a list is a mutable sequence, and you do have to implement those yourself. I don't want to go through all of the gory details of that, because it would be we could spend an afternoon doing that, and it's a fun exercise. But yeah, we would need to, and it's not going to let you instantiate them. So, and then if we look at, let's see, our ABC list won't exist, so I'm not even going to bother to do that. But then I can here check and see if my list that I inherited belongs here. It does. Actually, let's go back up here and look. My plain old garden variety list, A list, was, here, actually I can do that. Type A list. So here we go. Let's look at that, because that'll actually, so A list is a list, right? No tricks. Okay, if I go here and say, is A list a mutable sequence? And this answers the question you raised earlier. Yes, it is. And that's because when you actually use abstract base methods, there is the ability to register another class as being a subclass of the actual thing that you're creating. So in fact, list objects are specifically specified as counting as being, in effect, subclasses of mutable sequence. They aren't really, but when we use isInstance and we've got an abstract base class, we can lie and say they are. So that means we could actually create something that was, not really a list, but for all intents and purposes, we can make it be a list using abstract base classes. It is kind of a funky thing to play around with. And then if we look here, the MRO is the thing that you look at here. So if we look at what a mutable sequence does, you'll see that we get, I got ahead of myself again, dang it. You'll see that we get a list of the things that it inherits from. You can look at the Dunder MRO, the method resolution order, to see the things that it actually inherits from. Back when we were playing with classes, that's sort of what we ended up doing. You know, it's what will be looked at to find out, you know, where to get, for example, a bound method. And yeah, we're really sluggish today. I suppose someday I should actually reboot my computer, but I can't be bothered. So get up there. There we go. So you can see that these are all of the things that a mutable sequence inherits from object, from container, iterable size, collection, reversible, and if we go up a little bit more, all of the other ones. So yeah, it's actually an interesting way that sort of object-oriented programming in its more classical sense kind of interacts with Python and duck typing and being Pythonic. Okay, well, next thing I want to talk a little bit about is how to copy lists. And this may or may not surprise people, but I want to kind of run through this real fast. We talked about variables before, so a lot of this will end up being not too surprising, but you still might have to think about it a little bit. So if we want to copy a list, here. Let's say that we've got a list that itself contains some lists. So here, for example, I've got list 1 and list 2, and one of them is 1, 2, 3, the other one's 4, 5, 6. I could put those in another list that I'll call big list, and then I could copy big list into my list copy. Okay, well, let's go ahead and do that and just kind of set the stage here. So notice list 1 has this ID ending in 072, and list 2 has this ID in 912. Okay, that's cool. Now notice then that when I actually put list 1 and list 2 into big list, and then I get the IDs of first slot of big list, second slot of big list, same IDs. And then here when I do my list copy, since all I did was just this plain list copy equals big list, we learned this when we were doing variables as objects back in the first thing that I did. It's going to be just two different names pointing to the same objects. So big list, list copy are both going to point to the same object, and inside of that object they are both going to be pointing to the same two list objects. So everything is all the same. We can point that out too by just sort of having a quick look. And yeah, big list's ID is the same as list copy's ID, and the contents are the same. It's all the same. Okay, so then this will not be a surprise. What happens if I change the first element inside the first list in list copy? Instead of it being 1, I'm going to make it a 10. Yeah, Chuck, we have to come back to this. What happens? I mean, you are now armed with the special knowledge. You know the answer, right? Well, If I change the copy, am I going to change the original, yes or no? Well, so let's see it again. So yeah, in fact, they're referencing the same object. So you change one of them, you change the other one. Even though it's nested in a level, it doesn't matter. It's all the same. So that is not great. Okay, now I'm going to regenerate. This is the same thing. I'm just generating it again here. Um, and I made a couple more lists, and it's the same stuff, not to worry. Let's kind of get it down here. We got the same thing, and yeah, we always get, in other words, the same contents here. But if I want to actually make copies, then there is something I can do. And that is I can, from the copy module of the standard library, I can import deep copy. And deep copy is designed exactly for that particular case. And yeah, Chuck, I would agree. It can be really handy to just pass around different variables all pointing to the same object until it's not. So yeah, you need to be aware. But so if I import deep copy, I can make a deep copy of my list. And notice what I did was I actually made a big list 2, and we're going to make now a list copy deep. So basically my big list 2 is just like the other big list, except I just wanted to start fresh and not have that one hanging around. So I'm going to make a deep copy. Okay, if I make a deep copy, it looks kind of the same. Notice I've got, my various things floating around. But here, big list's ID is 0952, and deep copies is 7320. So while they look like they have the same contents, they have equivalent contents, but they no longer have the same object. Same thing. Actually, what we want to do here is we want to change that ID for list copy deep. 0. Get over here. We want that to be the deep copies first element, not the second. So that was a typo, but now we can see that. So basically, the first element, yeah, they're definitely going to be different here. So so we can do that. So now come back here. So now if we were to go ahead and change the first element of the first item in my copy, and I'll go ahead and hit that here so that we can keep moving. List copy slice is not, oops, I got ahead of myself. There, we changed, this is the place I was going. Okay, we changed that. We'll just change the one object because we have in effect created 2 different objects. And I wanted to do 2, big list 2, and so let's do it the right way. There we go. That was exactly why I created a separate list. So there, that actually works. Now there's another way we can copy, and that's using a slice. And this is kind of a weird compromise between the two. So you may be aware that if you're copying a list, you can use just a slice that is everything, and that will make a new list object. So when I do that, we can kind of see how that works, and we can see we got different IDs. So that's wonderful. The problem is that if we look at the actual contents, the contents are going to be a little bit different. So yeah, we got the IDs are different. That's great, but we don't have inside. We don't have different objects within. So basically here, let's go here. So yeah, we got, and I was doing that wrong. So here we can see a copy here of of list 0 is 480. If we go back up and look at what it is for big list up above, it's gonna be all the way up here. It's gonna be 480 if I can ever get there. Yeah, I don't know where I put it, but it is going to be the same object. So you can't use this copy trick, this list copy slice trick, to actually get completely new copies. Instead, all we got was a copy of the external list object. You know, that was done, but it was the two different lists are still pointing to exactly the same objects. Okay, let's see here. There we go. Well, okay, slice copy. And you see there, since they're both the same object, both in my list copy and my other one, we change both of them again. So if you've got mutable objects inside of a list, you need to be very careful about copying things. You need to understand what you want to do. And since we started talking about slices, I want to show you a little bit in our last few minutes about slices. So let me make a fresh list. It's still going to be called a list. And we all know things about slices. So you can slice explicitly. This would give us everything in the list from slot 0 up to, but stopping just before, slot 10. And since our highest slot number is actually 9, slot 10 would be the end, so we get an exact copy. That's cool. We can also use the -1 index to get up to the end. Oh, excuse me, no, that's not up to the, that's one short of up to the end, excuse me. And we can, if we don't want to specify the ends, we can get the whole thing by doing just the colon, sort of the empty slice notation. So that's cool. And of course we can do chunks using slices, not a surprise. And we can, if we specify a stride or a step value, we can actually, a third parameter here, we can actually control and skip things. So if I say that my step is going to be 2 rather than 1, I can get the odd numbers, actually, I suppose in this case, they're really the even number, but yes, the odd numbers up to slot 6, up to, but not including, slot 6. So that gives me that. And of course, you can, if you want, use negative values for your slices. So if I start at the end and go down by -1, I've in effect reversed my list, so I get a reversed slice. And we can even have empty slices. So if I say 1 up to but not including 1, that's an empty slice. Gives me an empty list. So cool. And then finally, I can do things where I actually set the value of one slice in a list to some other list. So again, here we saw that a list 1, 1 is going to be an empty slice. It's going to be the empty slice that is between the second and third slots. Or is it? No, it's going to be just before. Excuse me. It's going to be the empty slice that is just before the second slot. So we go 0, 1, 2, 3. This one is going to then be in the slot where the 1 is in our A list, right? So I can specify that slice and say, I want that slice now to no longer be empty. I want it to contain 1, 2, 3. So this will do an insert. And I remember that people saw this at there. So yeah, a slice is a copy of the list structure. It does reference the same elements internally. It's just a copy of the list structure. So it's not the same as a deep copy. So when I did this, basically, when I said I want to insert 1, 2, 3, my original list was 0, 1, 2, 3, 4, 5, etc. And I just said, okay, into that empty space before the 1, I want to put 1, 2, 3. So I now have a bigger list with that insert in there. And if I want to take that away, I can say, okay, I want those slots, those 3 slots starting from the second slot, I want those to now be empty. I want that slice to now be empty. And I can do that. So if that works, I should be back to my original list. I stuck them in using a slice, I took them out using a slice. The interesting thing of all of this is that slices, we use that colon notation in square brackets, but what happens is Python creates a slice object when it sees that notation. And lists, when you use a lists get item method, it looks for slice objects and then knows how to handle them. So a slice is a way of specifying a start, an end, and a stride, a step value. So you can go ahead and make slices. I just made a slice here. And they're objects. And they've got a bunch of stuff you would expect to see in an object. But they also have a start, a step, and a stop value. And that's what we look at when we're using them as slices. So in fact, we can say, yeah, all right, my slice, what is your stop value? Stop value is 3. And I can use this slice object here in square brackets, and it will be passed along to get item, and I'll get my slice back. So I can do that, and it works just fine. So it is a trick, and I owe this one to Luciano Ramalho and his book Fluent Python, but it is a trick that you can use, that you can make slice objects if it makes your code more readable, and you can pass those around rather than actually passing around the numbers if you happen to have some particular set of numbers that you want to use. Never really used that, but I think I'm going to try it. Okay, and then the next question is, well, can we actually do things like have multiple slices? Wouldn't it be a wonderful world if we could? Well, the answer in Python is no, you can't. But that's only for list objects. So here, this is kind of wrapping up my slicey stuff, but I'm making a class to just have an overridden dunder get item method to show you what you actually can do. So all this class does is, if you use square brackets to access it, it will tell you what it is it thinks you asked for. Okay? And I'm going to make a test object, and so first of all I'm going to see if I can do that. And since it's not a list object, it says, yeah, you asked for a tuple 1 and 4. Or if I were to do something like this, let's say I wanted to do 0 colon -1 colon 1, and I wanted to give it another set of indexes, and I want 2 colon 4 colon 2. Well, if I actually use colons, that would be good. Colon colon. Okay. Now, if I were to do this, here's an audience participation one. What happens? I'll wait. Well, or maybe I won't wait. I may be losing patience. We don't know. What happens is a surprise. Shrug emoji, I guess that works for me. Yes, ma'am, you are correct. You get a tuple of slices. This is by definition a syntax error if you're using a list, or if you're using like a user list. You'll get the same thing. It's going to complain. But if we were to make our own mutable sequence type object, theoretically you can do that. And in fact, I think NumPy uses it to handle arrays and things like that. So you do occasionally see this notation. There's nothing that actually keeps you from doing that. So in fact, you could. Here I was like, okay, so what I want to do is I want to make my own multi-list where I can have multiple slices, but even importing from user list won't do it. So it's kind of, it's like an exercise for the reader, as we used to say. And I might end up doing it one day myself just for the fun of it. It's like if you wanted to be able to do multiple slices, that would be what you would do. You'd make your own mutable sequence, and then you would implement getItem in such a way that if it got a tuple of things, it would then just be able to handle them tuple-wise, iterate through the tuples and get all of your various contents and etc. So yeah, NumPy does it for 2D arrays. And let's say, personal confession, I thought NumPy was somehow cheating, but in fact this is legal Python syntax as long as it's not a list or a tuple or something like that where it's predefined as a syntax error. But otherwise, you can do that. So this was an interesting thing about slices that I wasn't aware of until just recently when I started digging around for this episode. So it's kind of cool. And then to wrap things up, we can say goodbye with a little bit about tuples. Tuples are handy because unlike lists, they are not mutable. So in fact, they come from sequence, not mutable sequence, which means, if we go back over here and look at sequence versus mutable sequence real fast, which means they do not have methods like setItem, deleteItem, insert, reverse, etc. They don't have a lot of these things. They instead have just the bare basics: getItem, length, contains, iter, index count. They can be reversed, but they not in place. You can't have a reverse method that will reverse them in place. So that's really handy in that means they can be, since they're immutable, they're hashable, which means they can be the key of a dictionary or they can belong to a set. So if I want to make a 0.00, and let's say I've got a whole dictionary full of points and it has some value associated with each location. It could be a color value if you're doing something with an image, or it could be a number value if you're making your own spreadsheet. Whatever it is, you can go ahead and use tuples as keys in dictionaries, and that's darn handy. However, just because it's in a tuple doesn't mean that everything is immutable. Okay, you can in fact have a tuple of, and let me see if I can get this down a little bit more visible. You can have a tuple that itself contains mutable objects. If you have that, then you do not have that particular advantage. So if I make a tuple up here, you can have a list in a tuple, or my example here is having a dictionary in a tuple. If you do things like that, you cannot actually end up with it being usable as a dictionary key. So for example, yeah, here I did lists. So I've got two lists. I put them in a tuple. So I've got a tuple of lists. I have a tuple of lists. I try to use that as a dictionary key. It will hate me. It's like, nope, you cannot do that. Unhashable type list. So if you're using tuples as dictionary keys, they have to themselves contain only immutable objects. And then the last thing, you can use tuples as records. They're kind of handy that way because the order's never going to change, contents is never going to change. You want different contents in your tuple, you need to make a different tuple. So they're usable for records then. They don't have much machinery at all. You need to keep track of what field it is by which position it's at. But they're very stable, so they work great that way. But of course, if you want to do more with that, you can use a name tuple, which is in the collections library, and it basically lets you make a subclass of tuple that has named fields. So let me get a couple of these things out of the way. So I made a point class using name tuple. I said it's going to be point and it's going to have X and Y fields. All right, let me actually get these out of the way and do that. And so when you do that, basically you get a point object that has X equals 1 and Y equals 2. And I can do things like I can say, what is point.x? So I no longer need to say point slot 0. I can say point x or point y. And I get that. Or I can do it the old-fashioned way if I spell point right. I'll get there eventually. So I can actually reference it by slot number, or I can reference by name. So these are darned handy if you're fooling with records and you want to have that kind of ability to name fields so that it makes your code more readable, easier to maintain. People just sort of coming in to look at your code will understand what it is. So there are a ton more things we can talk about, but I hope this was interesting. I hope that you found slices as much fun as I did. Any final wrap-up questions? Because as usual, I've gone for like my 75 minutes, even though I swore I wasn't going to. So any final questions before I wrap this up? If you try to create a point with extra objects, you will get an error. Yeah, so like let's say I want to do a 3. Here it's going to be unhappy with me because I said we only had 2 points. So it's not going to know what to do with the 3. Quite right. Does using star to copy a list? Um, what star does is basically when you use star and pass it as a parameter, it breaks whatever iterable you've got into a series of individual items. Now, if you're talking about star for unpacking, I'm not. Star for unpacking would be a different thing in that basically what that does is you have in effect, the same sort of thing. You have a series of objects on one side that are going to be more or less equated to a series of objects on the other side. So that is pretty much just giving a different name to the same object. It's not really going to be a copy so much as adding a reference. At least that's my understanding. If you've got a specific example, we could test it out, but that's it. It's sort of the unpacking is just making a series of objects, making a tuple look like a series of objects on both sides. Yeah, I know. It's not really great to paste in an example. But yeah, in args2, it's like basically everything kind of gets turned in. So let's see. Yeah, in that case, it's really just turning your star L1 into a series of individual items in its components. So basically, you're kind of reconstituting that list, but we could see. Let's see here. So like we got L1 equals 1, 2, 3. And then, well, and good for you because that would be the way to tell. L2, I think it's going to be the same as like doing a slice copy. You're going to get the same effect. So we make a list out of star L1. Yeah, I would agree. That would be the same kind of thing I would ask. Oh yeah, I need to stop doing. Let me split this. So I'm just inheriting my error from above. Split cell. Okay, now we can go down and get the thing that we actually care about. So we do that. I thought I split you. Don't do that to me. There we go. There. But I think it's probably more interesting in this particular case to say, what do we get if we do this? Okay, so this I think might get at why you have different elements, different IDs. Can't use start expression there. Okay, yeah. So we actually need to convert it. But the thing that gets you a different list item is the fact that we've got the brackets around it. So what it's really doing is making a series of different elements. We're then putting the brackets around it to make it a list. So you're going to have the same items, but a different list object pointing at them. That's a good example, though. If I do this again, I will definitely throw in some playing around with that. Anything else? Yeah, L2 is going to be a different list with a different ID, but if we were to put like lists inside of each of those things, the contents, the actual things in the slots would be the same objects. That's I think, what happens there. So you don't do any sort of copying or anything like that. So it's kind of like using the slice copy or just the dot copy method. Yeah, they're all one and the same. Okay, any other questions? So yeah, in theory, it should be the same number one there. And we could go back up with my list of lists and try it out. I'm pretty sure we get the same result, but you can go ahead and somebody can go ahead and try it and let me know. Yes, okay, great. So we did check. That's kind of what I thought. Okay. So that's it for today. I will no doubt be back. I'm not going to commit myself to anything right now, but I'm assuming I will come up with something for next time. And in the meantime, let me kind of switch over to my going away screen. And we will be talking to everybody eventually. So everybody take care. Bye-bye.